let us see the stereochemical aspects of substitution reaction. So we already know what is a stereoisomer. When there is a difference in the spatial arrangement of atoms in a molecule, we call such compound as stereoisomers. Okay. So under that, we have some properties which will affect the reactions, like that is in substitution reactions. We will see some things will affect as per the stereoisomers. Okay. They are, one is your optical activity, second one is chirality, retention, inversion and racemization. So these are some points which we should know before going into the stereochemical aspects. Okay. First let us consider the optical activity. Okay. So what is this optical activity? See, we know that an ordinary light will have vibrations in all directions, that is the electric and magnetic vectors. So the vibration will have will be in all directions. Okay, like this ordinary light, which is basically your sunlight. Okay, when we pass this light, okay, where the vibrations are all in all directions, through a nickel prism. Okay, so this is basically a polarizer. This will filter all the vibrations except in one plane. Okay, so we will get the polarized, that is plane polarized light, where the vibration is in one plane. When we pass this plane polarized light through the solution of the compound which we want to know, so we fill this thing with the solution of interest. What will happen as a result is this plane polarized light might turn to the right side or left side, or it might remain the same. So the result what we get are of three types. Okay, if this plane polarized light is unaffected, see here the result is just like that in the same plane, then we call such molecules or compounds as optically inactive. Okay. Next one, if this plane polarized light turns to the clockwise direction, that is right hand side, RHS, or the clockwise direction, we call such molecules as dextrorotatory, or we also give the symbol D or a plus sign. Okay. Or the next one is, if this plane polarized light turns towards the left hand side, that is the angle of this thing will turn towards left hand side, or this is also the anti-clockwise direction. Okay, we call such compounds as levorotatory, or we also give the symbol L or negative sign. So we saw when the plane polarized light is rotated towards the right hand side, we call that isomer as a D isomer or dextrorotatory, or we can give the sign plus. Or if the plane polarized light is rotated towards left hand side, we call it as levorotatory, or we give the minus sign. Such compounds are optically active. Now, how do we find whether a compound is optically active? Okay, so the major points which we have to remember are the compound should possess a molecular asymmetry. Okay, next one is chirality, and the third one is it should be non-superimposable mirror images. Let me explain all these 3 points with an example, that is lactic acid. Here, if we see here, when we compare this carbon here, it has 4 different groups. Okay, 4 different groups are attached to this carbon. So this carbon is an asymmetric carbon. This carbon is an asymmetric carbon. Okay, now when we take this asymmetric carbon and we take the mirror image of this, so let me write the mirror image of this compound. So it will be COOH here, C, you can see the H comes this side, OH and CH3. Okay. Now, when these mirror images are are non-superimposable, that is, we take this molecule, just place it above this molecule. Okay, they are not non-superimposable. So, such compounds are optically active. Okay. So, when we find that the compound is not non-superimposable. This property is also called chirality, or this carbon or the compound is said to be chiral. Now let us see another example, that is butane 2-on. Okay. First let us see whether this carbon is asymmetric. Yes, because it has, this carbon has 4 different groups. Okay. Now we will see how to write the mirror image of this compound. So let us write this. The mirror image would be like this, that is HOC, it will be CH3, then C2H5, followed by H. So now if we take this mirror image of this one and just keep it on top of this molecule, so they are non-superimposable mirror images. So suppose let us consider this is the D form or the plus form, and this is the L form or the negative form. So this pair of isomers are called enantiomers. These are called enantiomers. Okay, that is, the 2 mirror images are called enantiomers. Okay. Suppose now we get, as a product of substitution, if we get both the D and L form, that is D and L form, 50 to 50. This is 50% and this is 50%, that is 50:50. Then we call such mixture as called Racemic mixture. And these compounds, because we have both plus form and minus form in equal amount, the optical rotation will cancel each other. Okay, as a result, racemic mixtures are optically inactive. Now let us see an example where a substitution is happening, that is a substitution reaction. It could be a nucleophilic substitution reaction. So let us take this compound where this carbon is chiral because it has all groups are different. Now if we substitute, suppose let us take this as a halogen, if we substitute this with another halogen or any other nucleophile, let us say Y, okay. Now imagine this X, wherever it is leaving, the Y is taking the same position here. So such compounds or such product is supposed to be having a retention in configuration. Okay, because wherever the X is left, there the Y is coming in, getting substituted. Okay. Now we have another product, that is, if this Y, okay, is the compound is completely inverting, okay, in this direction, and Y is attacking in the other direction, so we call this compound as the inverted compound, or inversion is taking place. Okay. So in nucleophilic substitution reactions, we have seen that, in for example SN1, both products can be formed in equal amounts. That is, let us consider this is A and this is B. If we get A plus B in equal amount, so this is the racemic product, racemic mixture. So we know that this will be optically inactive. Okay. Now if we go back to the nucleophilic substitution reaction and see, in SN1 reaction we found a racemic mixture was found. Racemic mixture was obtained, and in SN2 there was completely an inversion taking place.